Hello! In this video we are going to learn how to perform model order reduction of COMSOL state space models that are exported to MATLAB. Model order reduction will be explained on a particular problem of heat conduction that you can see over here. We are considering a plate, a thin plate that's heated by 9 spatially distributed microheaters placed on the back surface, and we assume that the temperature is sensed by 5 thermocouples placed at the top surface of the plate. In one of my previous videos, I explained how to export the COMSOL model to MATLAB. After exporting the model to MATLAB, we obtain the following state space description. Where, in this state space description, U is the vector of inputs. In our case, every entry of the vector U is the power applied to the heater. So this will be U1 and this will be U9, the power applied to the heater. And the model outputs are observed temperature. So the vector Y consists of 5 entries, where every entry is the temperature observed at the thermocouple. The vector X is the vector of temperatures at discretization points. So vector X basically consists of the temperature at the point 1 until T. I'm going to deliberately denote the last point 100,000. So the dimension of a state vector is usually in the order of 10,000, 100,000, or for finer meshes, it can go up to several millions. Now, if you want to design a controller, estimator, or if you would like to analyze such a model in MATLAB to check its stability or to perform some advanced analysis, you would definitely need to reduce the model order. So, after exporting the model and working with such a model, you will not arrive anywhere. So you need to apply model order reduction. Now, what you can see here in the corner, over here, is the sparsity structure of your system matrix A, and E has similar sparsity structure. B matrix is a tall matrix, basically it's a dense tall matrix, and C matrix is a fat dense matrix. These matrices do not play a significant role when it comes to computational complexity. Now, the model order reduction methods would like to reduce the order of your original model such that you obtain a reduced model having this form. Now, in this case, after performing the model order reduction, your reduced model order will probably be in the order of hundreds. If you can reduce the model, because some models cannot be reduced, but usually models, finite element models, can be reduced effectively. So our goal is to try to compute this state space model from our original state space model, where XR, the state of the reduced model, its dimension, let's denote it by like this, D, should be much smaller than dimensions of our original model. So in in vector algebra notation, if xr has dimension of d and x has dimension of n, we are searching for a model such that d is much smaller than n, while at the same time we want to make sure that our reduced model can accurately represent the simulations. That is, the output of the model simulated for certain inputs should match the outputs of the model simulated for the same input of the original model. So the reduced model should accurately represent the original model. That is, the input-output relation shouldn't change. What changes is the state basis. So the state basis will reduce. Now, our E reduce and A reduce matrices will probably be somehow, its dimension can be visualized as follows. Or they can be even smaller, as we will see later. They will be much smaller, in order of 100. So this will be our AR and ER, and this is our original model, A and E. We will effectively be able to reduce the model order. Now, what you can see here are the results. So our original model has the order of around 13,000. Here you can see the orders of the reduced model, and here you can see the simulation error. That's the error between the outputs of the large-scale model and of the reduced model. So we will see that the model of 256, or to be more precise, the model having 256 states, the reduced model of 256 states, will be able to accurately represent the input-output relationship of our original model. Unfortunately, the built-in MATLAB functions are not able to perform model order reductions of models having more than 500 states. So we need to search for an alternative, and I found one. And this alternative is called sssMOR Toolbox. This is a GitHub page of this toolbox. This toolbox is developed by people from Technical University of Munich. I tested the toolbox. It works surprisingly well on COMSOL models, and I highly recommend it. The model order reduction toolbox is accompanied by a conference paper, and I highly recommend you to read this paper before using this toolbox to get yourself familiar with basic functionalities and capabilities. I'm just going to explain one part of this toolbox. That is, I'm going to focus on modal order reduction, not modal order reduction, where we are going to search for a reduced model that preserves the first, let's say 50 or 100 dominant system modes. I'm positively surprised how modal order reduction works, how well it's actually working on the heat equation, and I highly recommend this toolbox. Okay, so here is the plan for this tutorial. First, we are going to learn how to model the system in COMSOL. We will learn how to define the probes, how to define the parameters such that we can easily export the model to MATLAB. Then I'm going to explain how to export the model to MATLAB. And then we are going to basically use the sssMOR toolbox to perform modal order reduction, and I'm going to show you some nice simulation results that I obtained. Here you can see the model order, not the model, the model order, we should be careful, and this is the error. This is the simulation error between the original large-scale model and the reduced model. And you will see that the model having 256 states is able to accurately represent the finite element model having 12,000 of state variables. And finally, I'm going to explain these graphs. These are basically simulation graphs comparing the outputs of the simulated and the original large-scale model. Okay, we start with explanation on how to model the system in COMSOL. So we click on New, Model Wizard. We are going to click on 3D. We are going to click on Heat Transfer in Solids. I recently used this module, so you can click on Heat Transfer in Solid. You click on Add. Click on Study. We are going to click on Time-Dependent Study. One second. So since my model is basically not being saved, the previous model. Okay, so this is our main window. So the first thing we need to do is to model the geometry. So we click on Geometry, we click on Cylinder, and we are going to choose the radius of 1 meter, and we are going to choose the height of 5 centimeters, and we click on Build Select. Okay, so here's our plate. This is our plate. We are not going to change it. This is how it is. Then we are going to define the input parameters. So in order to export the model from COMSOL Multiphysics to MATLAB, we need to define the inputs, and the inputs are modeled as parameters. So we are going to specify the inputs. This will be the input 1, and expression we are going to say, let's say 10 watts, and we are going to repeat this for other 9 inputs. In this particular example that I'm modeling, I'm assuming 10 watts of power at every input. However, you can later on scale the model, the StateSpace model, in order to obtain higher or lower power by just scaling the input. Now, the next step is to define the heat fluxes. So we are assuming that on the back surface, these inputs are acting. So we need to define the regions on the back surface, and we need to specify that at these regions the heat fluxes are acting. In order to do so, we need to define the work plane. So we need to define a work plane. We click on Geometry, we click on Work Plane, and we click on Build Select. So this is our work plane. What is a work plane? By defining a work plane, we can switch from 3D modeling to 2D modeling in a certain plane, and our modeling plane will be defined by z coordinate equals to 0. Now, we can click on plane geometry, and here is how our system looks in the plane z equals to 0. Now, we are going to define the regions. We are going to assume that the heat fluxes are acting at small circles of diameters, let's say 0.03 meters or 3 centimeters. So let us define these regions. The simplest way is to click on plane geometry and click on circle, and we can specify the radius of a circle, let's say 0.03, and we can specify the positions. Let's just leave it at 0, 0. Okay, so here's our circle. We need 9 circles, so we are going to just duplicate these circles we created. And the next thing we need to do is to specify the coordinates. So the first circle will be centered at 0, 0. The second one will be displaced at 0.3. So here's our second circle. The third one will be displaced at 0.3, 0.3. and so on. We can proceed to define all 9 circles, which I'm not going to show now in interest of brevity. So here are our 9 circles, and the next step is to define the heat fluxes. That is, we need to assign the parameters 1 to 9 to these circles. There are several ways to do that. In this video, I'm going to stick to heat fluxes. So I'm going to model the inputs as heat fluxes. You can also model them as boundary heat sources. In other applications, you can assume a thermal contact. You can consider inflow also, but I'm going to stick to heat fluxes. So I'm going to click on heat flux, and then the first step is to basically select the region. So here is our region. You have to be careful now since it's kind of like challenging to select it. Great. So here is the region 15. So the region 15 will correspond to our heat flux. And the next step is to specify the heat rate. Now, in our case, we are going to assign the parameter input 1 to this region, and we can click on build all. Notice that COMSOL knows when you specify input 1 that it is a parameter defined in the parameters section. Now we have to do a tedious job. We have to repeat this for all other 8 circles and parameters. There is a more elegant way, of course, to do that, and I explained this in one of my previous videos. You can basically export the model to MATLAB, and then using MATLAB you can write for loops, and these for loops you can just basically repeat the procedure that I'm doing it right now manually. But in this video we're going to stick to manual explanation. So the easiest way to do that is just to duplicate. You can duplicate the heat flux, and then you can basically repeat this to obtain 8 or actually 9 heat fluxes. And then for every heat flux here, basically you need to specify the region. Here in this case the region will correspond to, for the second one it will be over here, and the input will be input 2. Okay, after repeating this procedure for 9 times, we obtained 9 heat fluxes assigned to 9 circles, 9 circular regions, and you can check it over here. So this is the 15th one. This is basically the region 14. And you can notice here that for every specific heat flux we have a specific parameter set to it, and we have a region over here. You should verify that everything is okay and everything is fine, and then after that you can click on build all. Now the next step, of course, is to define the material. We click on material. We click add material from the library, and we can click over here on recently used materials, or you can select it from the material library. I have used aluminum in my previous videos, so I'm going to stick to aluminum. Here's the aluminum. These are the 3 important properties, material properties that you need to know for heat conduction. That's heat capacity at constant pressure, thermal conductivity, and density. Now, the next step is to define the probes. So the probes correspond to basically to the outputs of the model. So the probes are our thermocouples that we are going to place at the top surface. So I'm going to assume 5 probes. To get the probes, you click on definitions and you have the option probes. And we can select, oops, I didn't want to do this. You can select, you have several options to choose. And I'm going to choose domain point probe. I'm going to choose a domain point probe. You can of course choose other options. So what I'm going to do on the top surface, I'm going to assign 9 or actually 5 probes. So I'm going to stick to the z coordinate. The z coordinate is going to be basically the top surface, that's 0.05, and the coordinate of first probe is going to just correspond to 0, 0, and you can see it over here. The probe, you can see it over here, right? You just have to verify that this value corresponds to material thickness or to the height of your cylinder. That's true, fine. This is our first probe, and you define the other 4 probes. You can simply duplicate this one. And then you can specify the coordinates. You can choose the coordinates as you wish, but I'm going to choose the following coordinates. This will be 0.4. The other probe is going to be at 0.4. The fourth one will be at minus 0.4. And the final one is going to be at minus 0.4. And you can click on home, you can click on build all, but if you click on a probe, you can see it clearly here. This is the third one, and etc. You can basically see all the probes over here that you have defined. Great. Now we have defined the inputs, outputs of the model. The next step is, of course, to define initial and boundary conditions. So I'm going to stick with radiation boundary conditions. I'm going to choose surface to ambient radiation, since I want the heat to be dissipated through radiation mechanism. And here I'm going to assume the ambient temperature of 293 degrees, and I'm going to assume the surface emissivity user defined, since the aluminum in the library, by choosing the material from the library, this specific material does not have a surface emissivity that's defined. So I will specify the surface emissivity of 0.7. Okay, we have a surface emissivity, we have a surface to ambient radiation. However, you need to specify the region, so I'm going to assume the top, bottom, and the edges. Oops, it's kind of difficult to select since the model is very thin. And of course you can select these regions, but I'm not going to select them for simplicity. So the initial values, I'm going to assume the initial value of let's say 273 degrees. So I'm assuming that this plate is placed outside on a cold winter day. Okay, and we have basically defined everything we need to define. You can over here adjust the mesh size, which is always good. We are going to deliberately choose a fine mesh, since we want to have a large scale model once we export the model to MATLAB. And once you're done, you can click on build all, and under the study option you have time dependent, and here it's very important to choose the appropriate step size, since we are talking about heat processes, and heat processes are very slow. The time constants are usually in the order of for aluminum, heating of aluminum, we are talking here probably about 15-20 minutes once you apply step inputs to your system. So we are going to choose a range here starting from 0. We're going to get samples every 50 seconds, and the final time will be 1000 seconds. And we can simply click on compute. So it takes some time to obtain the results. I have a computer with 16 gigabytes of RAM, a laptop computer. COMSOL works relatively smoothly for smaller models. So these are your results. So this is the temperature change, very small temperature change, since our parameters are input parameters. We are considering 10 watts, and here you can see the time responses at your probes. If you click here are the time responses. To get more visible temperature changes, you can specify here, let's say 100 watts. Why not? So let's specify a few inputs to be 100 watts, to insert more power into the system, and let's see what will happen. So you click on build all, you click on study, you click on compute, and let's see what happens. Okay, you see immediately here, if you keep this window open, how in real time the results are being updated. So here are our results. Of course, these dominant inputs can be seen over here. These are your isothermal contours, and these are your probes. So we are talking about time constants, as you can see here, in the order of half an hour probably here, since these step responses still didn't settle. Okay, so the next step is to export such a model to MATLAB. Well, before you do that, it's very important to click here on compact history. Because if you export this model as it is to MATLAB right now, you will see that your code will be quite a mess. In MATLAB, when you open your code, you will see everything is upside down. Everything is randomly written. So by clicking on a compact history, you kind of compress your code in MATLAB. And how do we export the model to MATLAB? It's super simple. You click on Save As, and you're going to click on here on MATLAB, on actually an M file, and you can say MATLAB and you click on Save. Now, if you go now to MATLAB, you can click here on Open, and we can verify our model, right? Here is our model, and this is what you obtain once you export the model from COMSOL to MATLAB. So this is the result. Everything what we have written, or we have performed, all the operation we have performed in COMSOL graphic user interface can be done in MATLAB basically. So for example, here you're specifying the probe, you're setting the coordinates. So this is how we set the coordinates in MATLAB. So you can completely perform. I tested this, it works surprisingly well. You can do complete modeling in. I made a video on how to export models from COMSOL to MATLAB, and if these steps are kind of new to you, my advice to you is to watch this video. All the links are given in description below. Now, just briefly to comment, in order to export the model from COMSOL to MATLAB, you need a LiveLink for MATLAB. It's a COMSOL module. Then you need to start your MATLAB, but you need to make sure that it's connected to COMSOL. So to do so, you will basically need to start the program called COMSOL with MATLAB. Okay, now what we're going to do next, we're going to extract the state space matrices of the model. So we're going to raise here these function definitions, and we can just, for fun, we can just run the model in MATLAB. So by running this model, we're basically performing all the simulation steps in MATLAB. We're not going to plot here graphs in interest of time, that is to make this video as brief as possible. Now, the next step, of course, is to extract the state space matrices. Again, I made a video on how to extract state space matrices, and this video is available online, and its link is given in description below. So I'm going to wait a little bit. Now, what's happening? You're basically performing all the steps, however you're performing them in MATLAB. And since I've already written all the codes, I'm going to copy and paste the piece of code that's used to extract the state space model. So we're going to use the function mph state. We specified the model, right? We specify the computed solution, solution 1. We specify what we want to have as outputs. We want to have the mass, actually it's not the mass matrix. You should be careful here. These are our state space matrices. This is our E matrix of our model. This is our A matrix, this is the B matrix, this is the C matrix, this is the D matrix, this is the initial condition, and this is basically null space matrix, and this is a particular solution. I'm not going to explain this in more details. Look into my previous video, look into the COMSOL documentation for the function MPH state. Now, what is important to specify here? We need to specify the inputs. So the inputs are our parameters. You can see here are our parameters, and you can go back and you can look the code and you can search for parameters here. So somewhere here, actually over here, we have defined the parameters. So this is how you can define the parameters in MATLAB. It's much easier than in COMSOL, especially for models having, let's say, hundreds or thousands of inputs, right? Then you need to specify the outputs. Here are our outputs. So these are the probes. PPB1 is a probe. You can search for PPB1 just for fun to see how it's defined. Let's do that. Okay, so here it is. So here's your PPB1. You can specify basically the coordinates. You can specify for the second probe the coordinates, and etc. Right? Etc. You can define all the probes, and you need to specify here in MPH state that your outputs are defined by probes, by 5 probes. Next, you need to specify, you need to keep the sparse option on, because if you do not keep this option on, by default you will get a dense model having 20,000 state variables, and you will not be able to do anything with such a model. So it's very important to keep a sparse option on. And here are some other options that are related to linearizations, since basically this model is a nonlinear model. We are talking about heat conduction with radiation boundary conditions, and the boundary conditions are quite nonlinear, so you need to linearize the model. You can even specify linearization points. I'm not going to talk about that. And you can simply execute this line of code, and it maybe takes 10-15 seconds to extract the model. Let's wait a little bit. Let's see what happens. Great. So here is our model. I'm going to just extract the state space matrices. I'm going to just nicely extract them in EM, AM, because the COMSOL itself returns you a struct, right? And this is your, if you call m.mc, it will return your E matrix. I just, I like to deal with matrices. I don't like structures. And here finally we can visualize the sparsity structure of your EM matrix. And this is the plot or the graph you saw at the beginning of this video. So this is your EM matrix, its sparsity pattern. So this is the AM matrix, its sparsity pattern. You can see clearly that these are typical finite element matrices having a banded or band structure after performing Cuthill, probably McKee permutations, right? For those of you who are familiar with finite element matrices, you know what I'm talking about. And you can also visualize, it's very interesting to visualize the BM matrix, your B matrix, which will be here, over here. This is a tall matrix, since you can see that the state space dimension is, let's say, 13,000, and you only have 9 inputs. And you can also visualize the CM matrix. So here's our CM matrix. Again, it's a fat matrix. It's just a line having 5 outputs and having 13,000 states. Okay, finally I'm going to save the matrices. I'm going to save them in a file, And now I'm going to perform the model order reduction. So this is the main part of this video. I'm going to explain you how to perform the model order reduction. So what I'm going to do, I'm going to clear the workspace. I'm going to clear the workspace and I'm going to load the matrices. So here are matrices. Let's see, there should be in the computer memory. Here they are. We have AM, BM, CM, EM, and X0. This is our initial condition. Now, I'm going to use the toolbox called sssMOR. I mentioned this at the beginning of this video, why I'm using this toolbox. I'm not going to repeat it over here. And first I'm going to specify the model order. Let's start with the model order of, let's say, 2. Okay, this is our choice. We're choosing the model order. That is, we're choosing the state dimension of the reduced model. Now, with this command, so this command is the sssMOR command. It's similar to the MATLAB function ss, only we have an additional s, and we specify our model matrices. Since it's a descriptor StateSpace model, right, we need to specify EM. So this is our model. You can always type help SSS. Let's see what do we get. So this is our help, and everything is nicely explained. Descriptor matrix, sampling time, you can even define discrete time StateSpace models. You can do all sorts of tricks here, right? And then I'm going to use the modal order reduction method. Not the model, the modal. What are the modes of a system? The modes of a system. I'm not going to go more into structural mechanics or into control theory, but modal or modes of the system, you can think of them as dominant parts of your dynamics. So every system has, I don't know, thousands of modes, right? You can decompose this system into thousands of somehow independent models, and then not every mode is the dominant one, right? So you're basically looking for the most dominant modes of the system. Now, here's the function I'm using. So these guys from Technical University of Munich, they have coded the model order reduction. You can type help model or to learn more about this function. I think there is also online you can find a more detailed documentation. Of course, you can look into their conference paper describing this toolbox. Okay, so I'm going to perform the model order reduction. Here it is for the model having 12,000 states on a computer having 16 gigabytes of RAM, a laptop computer with i7 processor from 2017, and here it is. So what do we get? We get the reduced system description. If we just type SSR, what do we have? So here it is. Here's our reduced system. Okay, so this is your reduced A matrix, right? You can see second order. This is your B matrix. This is your C matrix. This is a D matrix. We don't have a direct feed through, and this is your E matrix. Notice the values of these parameters, 10 to the power 6. Now, the next step we are going to do, we are going to simulate. We are going to simulate the model, the original model and the reduced model for certain inputs. So I'm going to assume we can plot what kind of input I'm going to use. So I'm assuming, oops, this is not what we want. I'm going to plot input 2. Here is our input. Actually, I need to, this is a vector. I need to have, let's say, one column. Actually, this is not what we want. We want something like this. Okay. Let's see. So it's a typical random input to normal Gaussian distribution. And here how it looks. Okay. Now I'm defining initial condition for simulation. This is going to be just a 0 initial condition, and I need to define the sampling time. So I'm defining here the sampling time, right? This is our sampling time. Here it is. And I'm going to use the Backward-Euler method for simulating the original system, or actually simulating the original system and simulating the reduced system. Notice that people who wrote sssMOR Toolbox have implemented Backward-Euler method. However, you can do it by yourself. It's very easy, but here you have to be very careful since you're simulating descriptor StateSpace model. You cannot invert the matrix E. You cannot transform this model into the ordinary StateSpace model since you will lose the sparsity structure. So when implementing Backward-Euler method, you have to make sure that you don't invert matrices. This is a comment. And you can just perform the simulations. Here it is. Okay, it takes some time. And let's plot. Let's see what do we get. What do we get? Good. So what you can see here, the blue line is the output of the original StateSpace model for a random input. And the red line is the output of the reduced model for the same input. Here I'm assuming the second probe output, the output on the second probe, but you can choose any of 5 probes. So we can see that the results are not very good, right? The second order model is not able to represent the output of the original system accurately. So let's improve this. Let's increase the model order. Let's put it to be 16. And let's simulate everything. So we are simulating. Much better. So you can see that the 16th order model, this is the output of the 16, the red line. We can basically play with this line. You can change its thickness. So this is the red line is the output of the reduced model, and the blue line is the output of the exact model of the large scales model for random input. And then you can obtain even better results by, let's say, putting 128 as your model order. Let's see what happens if you have 128 model order. While the computations are being performed, I have to explain this line, this code line. Well, you're always interested how far is the output of your original system from your reduced model. So you can take the output vectors, simulated output vectors, you can subtract them, and you can compute the Frobenius norms, and you can divide them with the Frobenius norm of the output matrix of your original model, and you will obtain some relative measure of how accurately your reduced model represents your true model. So for this specific case, for 128, I obtain, let's say, 30% match. 30% match. Let's plot, let's see what happens for 128. Oops, we need to close this. Here it is, almost perfect match. You obtain almost perfect match. So the model having 128 states is able to relatively accurately produce input-output relationship of the original model having, let's say, 13,000 states. So you get the factor 100 reduction, and the error is still relatively good. Now, I have tested model order reduction for several model orders, and this is what I get. This is what I get from a specific example. Oops. Let me plot this. Okay, so what you can see here on this axis is the model order, and the y-axis you can see the relative error. So you can see that the model of 256 states reduced model achieves below, let's say, 20% of error, which is very good, which is very, very good. So these are final results, what I obtained. Here on these graphs you can see the outputs of the original system and reduced system for different model orders, starting from model order 2 to model order 256, and you can see how basically the accuracy improves as we increase the reduced model order, as we gradually increase. So somewhere here after 128 or after 64 we have very good match. And on this graph you can see the dependence between the error, the simulation error, and the model order. Okay, thank you very much for your attention, for watching this video. This is the longest video I made so far. I would like to thank people from Technical University of Munich for coding this modal reduction method and for coding other methods that I will test, and have a nice day.